This is LeetCode problem 34. Find first and last position of element in sorted array. Given an array of integers nums sorted in non-decreasing order, find the starting and ending position of a given target value. If target is not found in the array, return -1, -1. This is an example. We have a sorted array. The target value is 4. The first and last occurrences of number 4 are indexes 3 and 5. That's why the output is 3, 5. So that means in order to solve this problem, we need to find the lower bound of the target and also find the upper bound of the target. We can use binary search technique to find the lower bound and upper bound. The first step is to define the search space. The target could be anywhere in the array, so search space should contain all arrays indexes within range 0, length of nums -1. Step 2 is to narrow search space. If midpoint value is greater than target, then target is to the left of this number, so we should narrow search space toward the left. Right equals to mid -1. If midpoint value is less than target, then target is to the right of this number, so we should narrow search space toward the right. Left equals to mid +1. If midpoint value is equal to target, then there are two possibilities. 1. This is lower bound of target value. 2. This is not lower bound. Lower bound is somewhere further to the left. So we should narrow search space toward left to continue looking for lower bound, while also including midpoint itself in the search space. Right equals to mid. Step 3 is to choose an exit condition. The exit condition is left less than right. The while loop break when left and right pointer meet. The last step is to return correct value. The final value is the lower bound of the target. Now let's see how we find the upper bound of the target. Most steps are the same as how we find the lower bound of the target. The first step is the same, define search space. And the second step is very similar to narrow search space. It is exactly the same when midpoint value is greater than or less than target. The difference occurs when the midpoint is equal to the target. There are also two possibilities. 1. This is upper bound of the target value. 2. This is not upper bound. Upper bound is somewhere further to the right, so we should narrow search space toward the right to continue looking for upper bound, while also including midpoint itself in the search space. Left equal to mid. Now let's look at an example. The left pointer is at index 0, right pointer is at index of 12. Mid pointer equals to left plus right floor division by 2, which is index of 6. Now the midpoint value is equals to 5, which is greater than the target value, 4. So we should move the right pointer. Right should equals to mid -1, which is index of 5. Now the midpoint value is 3, which is less than the target value 4, so we should move the left pointer to the right. Left equals to mid +1. Now the left pointer should be at index of 3. Current midpoint value is equals to the target value 4, so we should move the left pointer to the mid pointer again. Now the left pointer is at index of 4. Then the midpoint value is equal to target value 4, so we should move the left pointer to the midpoint again. And now we're stuck in an infinite loop. When left and right pointers are right next to each other, mid pointer ends up being positioned where the left pointer is. Then we're stuck in an infinite loop. One way to avoid this loop is to bias the midpoint to the right by using mid equals to left plus right floor division by 2 +1. Now let's go back to the example. Midpoint value is equal to target value 4, so we should move the left pointer to the mid pointer. Now the left pointer should point to the index of 4. Mid pointer still equals to the target value 4, then we should move the left pointer again to the mid pointer. Now both left and right pointer are pointing to indexes of 5. We avoided an infinite loop with left pointer and right pointer meeting at the upper bound of the target. Step 3 and step 4 are the same. If the target doesn't exist in the array, the final values in both binary search algorithms won't be equal to the target. It should return -1. Now let's look at the coding part. We have two helper functions, lower bound binary search and upper bound binary search. Just like the steps we mentioned in the analysis part. We first define search space, then we narrow search space based on 3 different scenarios. One midpoint value is greater than target, less than target, or equal to target. If we find the lower bound, then we should return the left pointer. If not, then we return -1. The same for the upper bound binary search function. The only difference is 1. We bias the midpoint to the right. 2. We return red pointer if we find upper bound of the target. If not, then we return -1. And in search range function, we return lower bound and upper bound. Time complexity is O of log n, space complexity is O of 1.